a este evento. Good afternoon to everyone, and thank you for joining us in this talk. Today's talk is going to be about the future of hydrologic modeling, a sensitivity analysis, and a deep learning perspective. It will be given by Dr. Saman Razavi. Dr. Saman Razavi is an associate professor from the Global Institute for Water Security at the University of Saskatchewan in Canada. Dr. Saman Razavi, as I said before, works as Associate Professor of Hydrology and Water Resources Engineering at the Global Institute for Water Security at the University of Saskatchewan in Canada. And he's a licensed professional engineer with the Association of Professional Engineers and Geoscientists of Saskatchewan. His research work is at the science policy interface, bridging hydrological modeling and prediction of flood and drought to integrated management of water resources and decision and policy making. Dr. Razavi is also an expert in systems and data sciences, sensitivity and uncertainty analysis, and machine learning. Dr. Razavi has published over 50 peer-reviewed journal papers and has received several awards, including the 2020 Early Career Research Excellence Award from the International Environmental Modeling and Software Society, the 2019 Young Scientist Award from the Canadian Geophysical Union, the Water Security Research Excellence Award from the University of Saskatchewan, the Benjamin Maker Distinguished Visiting Professorship from the University of Bristol, and the Editor Choice Award from Water Resources Research. So it's really a pleasure for us, Dr. Saman Razavi, having you here. We were planning for him to come to Colombia at some point, but because of COVID, it was not possible. So we really acknowledge your commitment to make this talk virtually. Thank you for your time, and the floor is yours, Dr. Saman.
Thank you very much, Professor Rodriguez, for that very generous introduction. Hello, everyone. I'm very happy and pleased to be here, although remotely, and I would love to visit Colombia at some point soon, hopefully, say in 2 years. Before I begin my talk, so as you might say, the title of my presentation is perhaps a bit ambitious, and a disclaimer that I'm not here to say how the future of hydrologic modeling should look like, but I'm going to provide some perspective on what I have been doing, in particular recently, around deep learning and sensitivity analysis. And you know what, again, I was, I guess, overly ambitious when I gave this title to you, but when I was working to put together my slides over the past couple of weeks, I realized, wow, there is a lot of materials to cover. So I ended up basically narrowing down a bit on deep learning. But if there is interest on sensitivity analysis as well, I could say something about that. And of course, I would be more than happy to have any follow-up conversation or talk or whatever to build more on whatever I'm talking about, in particular sensitivity analysis that is going to be missed a little bit here. So, as I said, I'll be trying to provide some perspective on past and future research efforts to leverage new advancements in data science, particularly around deep learning and sensitivity analysis. So most of materials today are based on these two recent papers that I'm showing on the screen. One is an in-depth look at the what's and whys of deep learning, its fundamentals, explainability, and bridgeability to process-based modeling. And this paper is now under consideration in reviews of geophysics, but it's open access. You could go and download it from this website. And the other one is a community perspective, the one to the right, on the future of sensitivity analysis, drawing from views and expertise of a multidisciplinary team from natural scientists, engineers, decision scientists, computer scientists, systems analysis, and mathematicians. That was the outcome of a one-day workshop back in 2019 as a satellite event to SAMO, basic sensitive analysis of model output international conference. So here's the motivation and objective of this talk. Many of you might have heard about deep learning, in particular these days, which is an artificial intelligence technique that already served a vast majority of us, if not all, at least through our smartphones, in tasks such as image recognition and natural language processing. Those applications naturally have shifted our attention in earth and environmental sciences and relevant funding agencies towards deep learning and machine learning and AI in general. And let me give you some numbers about this shift. About 5% of presentations in the last AGU fall meeting, American Geophysical Union, this past December, were on machine learning, 5%, while this figure was only around 0.2% just a few years before, in 2015. And when you look at the years from 2015 to the 2020, you see a consistent rise in the numbers. And the hydrology section in particular that I belong to was one of the front runners with this shift, with about 7% of presentations on machine learning this past AGU. And now there's a challenge. Of course, earth and environmental sciences to date have been dominated by a knowledge-based or process-based modeling paradigm, which is fundamentally rooted in a different worldview than that of deep learning. So this limits the bridgeability and cross-fertilization of the two modeling paradigms. With the challenge in mind, the overarching objective of this talk is to contribute to an AI-assisted modeling paradigm for earth and environmental sciences, where deep learning can embrace the typically ignored knowledge base available, function credibly in true out-of-sample prediction, and handle non-stationarity in earth and environmental systems. So throughout this talk, I'm going to try to cast more light on what I mean by each of these sub-objectives. So let's step back for a minute and think what AI is and what it is for. Here is a recent definition of AI on the top. AI is concerned with developing machines that improve their own performance in carrying out a given task over time by learning from examples with minimal human efforts to instruct the machines how to do so. And of course, this is a very recent definition. And when you look at the definition of AI over the past multiple decades, it has changed really significantly. And if you wonder how the AI community evolved to get to this definition, a textbook by Goodfellow et al. 2016 says it very nicely. So according to them, the early efforts to generate AI were based on a knowledge-based paradigm to instruct machines with a formal set of step-by-step mathematical and if-then rules. For example, think of instructing someone or a computer how to play chess. You can do it by a set of if-then rules, right? And basically say, oh, these are the pieces, these are the rules, this is what you can do in different circumstances, and that's it. But those efforts focused on carrying out tasks that were intellectually difficult for humans, but straightforward for computers. So going back to the chess example, it might not be easy for you to quickly think of all possible combinations and scenarios that a game may lead to. But a computer can do that very quickly and evaluate all possible scenarios in a fraction of a second, and then basically make the best decision based on all the uncertainty. So such efforts led to no major success, according to Goodfellow et al. And AI of today is something else. It's about enabling machines to perform tasks that humans perform intuitively and easily, but have difficulty formally describing how they do so. For example, think of recognizing a face in a photo. For example, you see your friend in a photo, you quickly recognize. But you can do it easily, but it's not easy to come up with a set of rules that the computer can follow and do the same. So you do it intuitively and quickly, but it's hard to come up with a set of if-then rules, for example, to teach someone else or a computer to do a similar thing. That is about AI of today. Another point is that not only did the state-of-the-art AI divorce from knowledge base, but it also completely separated from classic data-driven modeling, rooted in statistics, such as regression. What do I mean here? We know that traditional statistical modeling requires a formalization of relationship between variables and assumptions about functional aspects, functional shapes, for example, linear or polynomial, or about distribution of variables and their interdependencies. And when we have those, those enable us to do hypothesis testing and also generate confidence bonds on our predictions. In many real-world applications, the underlying relationships in data may have any complex form, and the data used may have any size and distributional properties, all of which can be unknown a priori. So in such context, DL can be useful because DL or deep learning models are not constrained by the many assumptions that typical statistical models hold. So it's free of a lot of assumptions, and that's good. That's the motivation mainly for using these techniques. And because of all these characteristics, deep learning is now deemed suitable to pursue the long-standing ambition to build machines that work with minimal or no human supervision and imposed assumptions. As a result, deep learning provides hyper-flexible tools that can be applied across a wide range of problems. And that is what's happening now. So what is deep learning? For 5 minutes or so, I'm going to explain what it is and its evolution over the past 30, 40 decades to this point. Deep learning models are nothing but artificial neural networks that have been around for decades. So many of us have been working with artificial neural networks in the past 20 years or more. It's made of small processing units called perceptrons or neurons because of its resemblance to the basic working unit of the brain. And what you see on the left of the screen, a neuron receives multiple inputs, x values here, and multiply each by a set of weights. Then the weighted sum of all those go to an activation function, which is typically nonlinear, and it produces the output of that neuron, that is y. So when you look at the formulation of a neuron to the right, you see it has d plus 1 tunable parameters, basically d weights and 1 bias. And it's basically nothing but a multiple linear regression. That's what you see inside that bracket. That's a multiple linear regression augmented by an output function, and that function f is nonlinear. So now that we know the building block of ANNs, or artificial neural networks, basically neurons, let's quickly review its historical evolution since inception all the way to now. So the invention of perceptrons back in 1950s created significant excitement in the AI community and beyond. But it soon became clear that a perceptron would not be able to map input spaces that are not linearly separable, such as X or problems, if you've heard of them. So basically rendering perceptrons of limited use in real-world applications. So the reason for this inability is that the core of the perceptron is a linear regression, as we just saw. So back then in late 50s, different ideas were tried to address this issue, but the most viable one was to combine perceptrons both in parallel and in series to create the so-called multi-layer perceptrons, or MLP, and that's what I'm showing to the right, with the hope that this more complex system could overcome the barrier. An MLP would then have many more tunable parameters, many more weights and biases, basically, than the perceptron. The total number of layers in an MLP, so you can have many layers, and the number of neurons in each layer are hyperparameters to be specified by the user. So you have to basically come up with some structure that works for you. And MLPs, but here's the point, MLPs on their own did not go far, and the field stagnated for many years because of the absence of an algorithm that could automatically derive from data the network weights and biases. So it took until the mid 1980s when the first backpropagation algorithm was invented to enable the training of MLPs with any network structure. This invention marked the beginning of the second wave of popularity of ANNs. Soon after, MLPs were proven to be universal function approximators, and this proof indicated that MLPs with only one single hidden layer that possesses a sigmoidal activation function, those nice S-shaped function, and a linear output layer would be able to approximate any function with any desired level of accuracy, provided that the number of hidden neurons is sufficient. Since then, the universal function approximation theorem has been the fundamental driver of interest in MLPs across a variety of disciplines and applications because it tells you it can approximate anything. So at that point in time, also different approaches were developed to introduce memory and time dependency to ANNs. Different ideas appeared to do so, such as tap delay lines and time delay neural networks, recurrent connections and recurrent neural networks, and the idea of information gates, and basically long short-term memory or LSTM networks that are now very popular in hydrology. This is also the point when ANNs started receiving much attention in earth and environmental sciences. The first publications around ANNs in water resources started appearing in early 1990s. But despite all these advances to this point, investments in ANNs and therefore popularity of ANNs saw a decline in the AI community beginning in mid-1990s. Perhaps triggered by failures to fulfill overly ambitious or unrealistic promises by some prominent AI scientists, as historically observed in AI winters. And I want to draw your attention to this term, AI winters, which are very important to know about. They have been pretty common in the history of AI technologies. An AI winter is a period of reduced funding and interest in artificial intelligence research. And the amplitude of these waves and periods have been pronounced, perhaps compared with any other fields of research. And of course, any field might have ups and downs, but AI has been really pronounced in that sense. And I think that the reason for that is AI relates to science fiction, which we as people get quickly quite excited about. But the field has also been filled by overexcitements, overpromises, and oversellings. And whenever there is a failure in delivering those promises, a major decline in funding and investment followed. And there is quite a bit of literature on that, on AI winters, and its what's and whys, and a good source to begin with on that. If you want to read more about AI winters, refer to Wikipedia, but there is a lot online. I should also add that during this decline period, ANNs in earth and environmental sciences remained fairly popular, arguably until mid-2000, and the focus of researchers in these fields was to find novel applications of ANNs across different earth and environmental science problems. Anyways, it took until early 2010s before the third wave of popularity and interest in ANNs hit, when the field was revived and renamed or rebranded as deep learning, and that is the era we now live in. So what does depth mean? Depth is a recently popularized term and that loosely refers to the number of hidden layers in neural networks. And a related term is width, which loosely refers to the number of neurons in hidden layers. So now a deep learning model or deep neural network simply refers to an MLP that I just showed you with 2 or more hidden layers. So before we review a couple of major recent milestones, consider the fact that the structure, formulation, and other properties of MLPs have remained unchanged since inception, except for some minor modification. So basically, the MLP network that I'm showing on the right bottom of this slide has remained unchanged since inception. That's very important. So what is really new? Why it has been rebranded again? And for those who used neural networks before, say around until 10 years ago, but haven't followed the recent literature, it might be surprising a bit to see the tremendous revival of neural networks. And they might ask, what did derive the recent rise of neural networks? What was the problem that is now resolved? And is deep learning merely a rebranding of what existed before? So these are some of the questions that I had myself, and I tried to find some answer, and I'm going to share them with you. So to address these questions, we would need to discuss what historically drove interest towards ANNs with single hidden layer, while example applications of many layer perceptrons, or nowadays so-called deep learning or deep neural networks, have been around for 3 decades at least. I can think of 3 reasons. First is the universal function approximation theorem, as it provided a compelling argument that such neural networks are fully capable of learning any function. Second, the principle of parsimony, as neural networks with fewer hidden layers are generally deemed less complex and more understandable. And the third one is the difficulty of training, as neural networks with more hidden layers are more complex to train. So people historically try to stay with the neural networks with a single hidden layer for these reasons. But nowadays, neural networks have many more hidden layers, sometimes hundreds, with hundreds or millions of parameters. Huge networks. So what has changed really to make this push for deep neural networks? I would say it is all about difficulty of training. Training of deep networks has been actually made much easier in the last 10 years or so, and that has been the driver, as far as I understand. So how the beginning of this shift or change in making the training of networks easier is commonly attributed to the work of Hinton in 2006, who is a prominent computer scientist out of University of Toronto in Canada, where an unsupervised learning was used to pre-train deep neural networks. They showed unsupervised learning could effectively initialize the network's parameters, such that the subsequent training efforts through BP, backpropagation, would become more successful. I will not explain here what unsupervised learning means in this context, and I will say, all I say is that it is some heuristic way of layer by layer training. And that pre-training approach has now actually been abandoned. That's important to know. Instead, the booming computational power has actually made the old BP algorithms capable now of training deep neural networks, even with millions of parameters. And a game changer for that was the introduction of graphics processing units, or GPUs, to the neural network community as a powerful tool to massively parallelize and expedite the training algorithms. And also the investment by mega companies such as Google and Facebook in this field might have explained the revival of neural networks, resulting in huge successes in image processing and speech recognition, as you do with your smartphones. So with that intro and literature review, I'm going to discuss how deep learning is similar or different from process-based modeling. And that is a question that many of us might ask. Machine learning has been extensively used to model systems for which knowledge-based or process-based or mechanistic models are also available. And that is what's happening now in hydrology as well. In the hydrology context, the fairly large body of literature now benchmarking machine learning techniques or deep learning techniques against process-based models. And process-based models are based on the physics governing the underlying processes and are therefore typically evaluated based on both their physical realism and goodness of fit to data. However, machine learning models does not do much, if anything, with the underlying physics, while reportedly they do a superior job in fitting data, even in out-of-sample prediction. So what do these all mean, and what are the implications? We need to consider that deep learning is rooted in three things. What I refer to as connectionism, hyperflexibility, and vigorous optimization, which are fundamentally different from the guiding principles of classic process-based modeling. And these differences are often ignored, but they must be considered at the heart of modeling efforts that use deep learning in earth and environmental sciences. So what do I mean by these three things? Connectionism is an approach that stacks many identical or similar algebraic operators, both in parallel and in series, like neurons and multi-layer perceptron that I just showed, in parallel and in series, that can collectively perform complicated tasks. In this approach, the roles and functions of different individual operators in producing the model response are not distinguishable, unlike the modular approach typically adopted in process-based modeling, where each part of a model is designed to represent a specific component of the system being modeled. As a result, considerations of identifiability and equifinality of model structure and parameters become irrelevant in deep learning, in the sense that for a given problem, there will never be a uniquely identifiable model, and there can be an almost infinite number of equifinal models. Hyperflexibility is a characteristic of a model that can literally fit any data set with any desired level of accuracy, owing to its excessive degrees of freedom. Of course, neural networks have excessive degrees of freedom. So hyperflexibility appears to be inconsistent with Occam's razor, or principle of parsimony, which has always been a guiding principle in scientific discovery and model building. Also, a hyperflexible model like neural networks are controlled by parameters that possess no physical meaning, unlike process-based models that have limited degrees of freedom controlled by parameters that possess some physical meaning. And last one, vigorous optimization is the practice of manipulating model parameters at any cost to maximize the goodness of fit to data. This practice is core to deep learning. Process-based modeling, however, uses optimization largely to fine-tune model parameters with the ultimate goal of improving model realism. As such, physical consistency of model parameters is irrelevant in the context of deep learning, which is a critical consideration in the context of process-based modeling. So coming back here, so what? What did we learn from these three principles? What we could say is that overall, these three characteristics make deep learning uniquely suitable to handle possible correlations of any form embedded in any data set of any nature, to build complex mappings in high-dimensional spaces. As such, deep learning can relatively easily scale to any data type and size in terms of both the number of variables involved and samples available. On the other hand, process-based modeling is generally based on causations, presumptive or real, derived from the existing knowledge and experience. Also, the modular nature of process-based modeling allows for hypothesis testing and testing about hypothesis development and testing about different processes involved in a system, something that you cannot easily do with deep learning. However, this ability can sometimes render difficult the scalability of process-based models to different data sets, which in cases require altering the model structure and parameterization. Also, deep learning models are inherently black boxes, and this is a major disadvantage, particularly when compared with process-based modeling. Of course, a deep learning expert can see and synthesize the model parameters and internal signals of a deep learning model and characterize their properties, such as their distributions and dynamics. Nevertheless, it's not trivial, if possible at all, to make sense of why a deep learning model behaves the way it does and how it may respond differently to different perturbations, and more importantly, to explain those to a stakeholder. Conversely, the behavior of process-based models, even under unseen circumstances, tend to be more explainable and intuitive, supported by the knowledge base available. So to elaborate on some of the points that I discussed, I'm now going to walk you through a modeling experiment that runs and compares both types of models for the same problem. This experiment models the hydrologic system of the Oldman River watershed in Alberta, Canada, with an area of almost 1,500 kilometers. So a simple case study mainly for educational purposes. Data and models. On average, this watershed receives about 600 millimeters of precipitation, meaning rainfall and snowfall, annually. It has a long-term average temperature of 2.2 degrees Celsius, and as you see, so it fluctuates quite often around the melting threshold, and generates about 12 cubic meters per second of river flow on average. Here we use 30 years of data. The first 20 years were used for model calibration, that is the seen data in model development, and the last 8 years for model validation, that is the unseen data in model development. And the first 3 months of the calibration period were used for model spin-up. In the case of deep learning, the calibration period was further broken into training and testing. And testing, basically 70 years for training, 5 years for testing, the latter for early stopping of the training process to avoid overfitting. I'm not going to explain what early stopping is, but that's the strategy used in training a neural network. I should note that the naming convention in the deep learning context for validation and testing period is often the other way around. So if you are a neural network person, typically you call this period validation and this period testing, but that's just a naming convention. So to model this system, we use a standard LSTM, or a long short-term memory neural network, that accounts for time dependency. And that's state-of-the-art deep learning model basically for these type of purposes. And the LSTM configuration model we use has 166 calibration parameters. And for benchmarking purposes, I use the HBV model, which is, of course, a classic and well-established hydrologic model with only 12 parameters. And each of the parameters of HBV has some physical interpretation and a physically justifiable feasible range. And the inputs to the models are daily precipitation and temperature, as I'm showing on the screen, and the output is the concurrent flow. The calibration of the two models were done by maximizing the goodness of feed-to data by evaluated by the Nash-Sutcliffe efficiency, or NSE, as the objective function. As you know, NSE is essentially a normalized version of mean squared error, and NSE of 1 indicates a perfect fit, and as a rule of thumb, Hydrologists often call an NSE of 0.7 and higher an acceptable fit. So you want to go up as much as possible. The LSTM model was calibrated using BP with the early stopping strategy to avoid overfitting. And the HPV model was calibrated by a multi-start Newton-type optimization algorithm. So I'm not going to explain what they are. You have to just trust me on those. And then 5 independent replicates of calibration experiment, basically with different initial random seeds, were conducted to account for possible variability of model performance. So basically, just running each model once with some initial random seed may not do work well for us because there is a lot of sampling variability in calibration and training problems. We have to account for those by running the same experiment multiple times and look at the average behavior. And the plot to the right compares the performance of HPV with that of LSTM in calibration. So the figure shows all 5 replicates of LSTM outperforms those of HPV. All of them are higher, and their average, of course, is higher. So based on these results, the superiority of LSTM over HPV in calibration is quite significant from a hydrologic modeling point of view. Okay, that was a calibration. And before checking models in validation, let's step back and investigate what we have achieved in terms of learning from data for both LSTM and HPV models. The development of the LSTM model was not based on any prior knowledge of how a watershed system works and the governing physical principles. As such, the model learned everything from scratch, merely using examples from data. Basically, the model started with a fully randomized internal configuration controlled by a large number of parameters, in this case 186, and then tuned those parameters to adopt the internal functioning of LSTM to the underlying real-world system. To better see that, let's look at this plot, which shows the LSTM performance of 2 arbitrarily chosen replicates before and after calibration for a 2-year sub-period of the calibration period. The model response to inputs before calibration seems to be completely random, as you see. But after calibration, the model response has learned to closely follow the underlying response. And that is the blue line that you see, very closely following the observation. But unlike LSTM, HPV encodes the expert knowledge available in the field of hydrology. This model is a collection of conservation of mass equations and process parameterizations that represent how hydrologists conceptualize the way a watershed works. This physically based modeling structure is presumably able to emulate the behavior of any watershed by tuning only 12 parameters, as opposed to 186 parameters. This other plot to the right shows how the model performs before calibration with parameter values chosen to be at the midpoint of their ranges and after calibration. The figure shows the uncalibrated model responds reasonably to the inputs. It generally captures the timing of flows and emulates the low flow segments but is overly responsive to large precipitation events, generating spurious spikes in flows. But calibration, the blue one, either by manual calibration, expert knowledge, or automatic calibration, like optimization that I did here, can fix the discrepancies and feed the model output to observations. So a fundamental difference between the two approaches is now clearer. Using a process-based model is about directly using a wealth of expert knowledge available in a scientific field, while using a deep learning model is about learning everything from scratch directly from data. And this difference is manifest in the number of parameters that need to be tuned to achieve a reasonable performance. And as we saw in the previous slide, the LSTM model achieved a better performance in emulating observation after calibration. However, in any modeling exercise, one needs to ensure that the model gives the right answer for the right reasons. That is why proper model evaluation in out-of-sample prediction is critically important, and as I'm going to discuss in the next slide. Okay, so we have already looked at model calibration. Now let's look at model validation. In general, we know that validation and verification of mathematical models are very challenging in some scientific disciplines, in particular hydrology, if possible at all. And the standard practice is to test the performance of the model in terms of reproducing some historical record not seen during model calibration, a process typically called out-of-sample prediction. So the plot to the right shows the results of such practice in validation period for both the LSTM and HPV models. In this case, both models do reasonably well from a hydrologic point of view, but LSTM outperforms HPV across all the replicates. So here I have LSTM performance in validation versus HPV. Again, LSTM is doing better. And consistent with what we just saw, the hydrologic literature is full of such conclusion that ANNs, neural networks, are superior to process-based models in both calibration and validation. But is this really the end of story? All my argument in this talk is that I would say no to this question, and we need to look deeper. So the problem is the above so-called model validation is inherently partial, as nicely articulated by Naomi Oreskes 30 years ago. While the performance of LSTM here appears to be better than that of HPV in a relative sense, one needs to take extra care before making such a conclusion. And as argued by Vid Klimesh back in 1980s, the prominent hydrologist more than 3 decades ago, a strong assumption in this type of validation is that the conditions under which the model will be used will be similar to the conditions under which the model has been developed and calibrated. But it's now well recognized that such an assumption may not hold, as many natural systems are essentially non-stationary. And despite such recognition, this standard model validation practice has remained arguably unchanged. But we have to do something about it. So what can we do? Here, I'm going to take a sensitivity analysis approach via a what-if scenario question to test and compare the performance of both models in what I refer to as true out-of-sample prediction. Basically, under conditions that have not truly been seen in the process of model development and calibration. So the question I'm going to investigate is how the system would behave if the average temperature warmed up by 2 degrees Celsius while everything else remains the same. So to assess this question, both calibrated models were fed a new temperature time series obtained by adding 2 degrees Celsius to all daily temperature values. So now the historical average temperature is at 4.2. These new inputs roughly provide a picture of what might happen in this watershed under global warming. That's a very important question, a climate change impact for many of us, right? And the modeling results under such scenarios are typically used to inform policymaking for climate change impact adaptation. So very important research question. Now let's evaluate the possible changes in the watershed behavior in response to a 2 degrees Celsius warming based on the two modeling paradigms. Here, instead of looking at the individual simulated time series as I did before, I'm looking at the possible change in the average seasonality of flows. So average seasonality of flows over a year, that's what you see. And let's first look at this plot to check the consistency of simulated flows for historical periods. So for the historical record, no scenario analysis. The black line was the observed seasonality. And now the red envelope that you see is the output of LSTM. And you see an envelope because we had 5 replicates. And we can similarly look at the envelope generated by HBV. So both models generally follow the observed seasonality in historical period, but the range provided by LSTM model is generally narrower and better encapsulates observations in both low and high flows, but they are pretty comparable. Now a look at the condition under the new future scenario is important. So for the hypothetical or future scenario case, I'm plotting the response of the 2 models. Again, the red envelope now is the LSTM response under the what-if scenario, but the blue one is the HBV model. Under the new condition, the 2 models show 2 distinct behaviors. This is very important. According to LSTM, peak summer flows would decline by about, say, 25%, and the time of peak would shift backward by about a week. But according to HBV, the change would be much more pronounced. The peak flow would decline about 35%. And the flow might show 2 modes, the larger at the beginning of May and the other one at the beginning of June, so perhaps around a month earlier. So as you see, these 2 models are quite diverging under a situation that haven't been seen in the historical record. So are such differences not sufficiently large for us so to make us skeptical about the modeling process? So that's a main question here that I'm trying to address, of course not answer, because it's very difficult to answer to these type of questions. But before getting to that question again, let's do something else as well. Let's try to inject some physics into deep learning, because one may wonder, what about possibility of ensuring that deep learning results are physically consistent, particularly under new conditions? So here is how I'm going to do it. Let's recast the modeling problem based on some understanding of the governing physics in hydrology. For example, physics tells us that the freezing point of water is around 0 degrees Celsius. And therefore, this threshold could be used as an approximation to differentiate rainfall from snowfall on a daily basis. And if the temperature on a day is above or below 0, then the precipitation on that day would be rainfall or snowfall. So I had so one of the inputs was total precipitation, which was summation of rainfall and snowfall. But now I can use the temperature time series to differentiate rainfall from snowfall. And this differentiation is actually a part of the process parameterization in HBV. Similar to many other hydrologic models, there is a parameter called temperature threshold for melting, freezing, and separating rain and snow. And its feasible range is from -4 to +4 degrees Celsius. And the warming of a watershed would naturally change the rainfall to snowfall ratio. And so building this domain knowledge into the LSTM model makes sense. So, and perhaps the most straightforward way of introducing this temperature threshold concept to LSTM is via pre-processing of the inputs. Therefore, a new LSTM model was developed here and calibrated, what I'm referring to as process-informed LSTM, with 3 inputs now: rainfall, snowfall, and temperature. So whatever total precipitation data I have, I look at the temperature and separate that to rainfall and snowfall. And now for the future condition, I can do the same, and I can change the precipitation or rainfall to snowfall ratio for my future scenario as well. So the plot to the right, bottom right, show that process-informed LSTM and standard LSTM showed very similar performance. Oh, sorry, I'm not showing that here. Process-informed LSTM and standard LSTM showed very similar performance in calibration and standard out-of-sample prediction. I'm not showing that here. But what I'm showing here is the performance of the process-informed LSTM in the true out-of-sample prediction. And the process-informed model now generates rising and falling limbs that are more consistent with those of HBV in terms of timing. So according to this one, the summer peak flow would decline by 20%. On average, perhaps not much different than the standard LSTM, but the time to peak, or basically the melt time or snow spring freshet, is appearing about 1 to 2 weeks earlier. So by introducing this physics, my process-informed HBV model got closer a bit to my HBV model. But still, you might say the result of HBV and LSTM, process-informed LSTM, are still quite different. So perhaps this injecting physics still quite far from process-based modeling. So a question then is, what model should we trust, deep learning or process-based? Which one of the three models here produce the most credible picture of possible watershed behavior under the new conditions? So we know that in practice, this is a very difficult question to answer, if possible at all. And in general, the prediction of such changes can be debated and might vary from one study to another, depending on the model used and the data used. And perhaps a definite answer would need to wait until the future has come and shown such possible changes. And from a bigger picture point of view, models of natural systems cannot be verified or validated in true out-of-sample prediction because those systems are never closed and not everything can be represented in a model, as argued by Naomi Oreskes back in 1990s, the paper that I showed you earlier, or the reference that I showed you earlier. But as scientists, we have our own perceptions and intuitions. These might be biased, but still useful to provide a ground for building confidence in the credibility of a model. In the context of the case study given here, previous research on the Canadian Rocky Mountain has indicated that the warming alone will result in a considerable reduction in flows and earlier peaks in watersheds similar to the Oldman watershed that I simulated here. A synthesis of research efforts under the Changing Cold Region Network, a major project in Canada in this region, showed a shift in timing of the spring hydrograph rise and peak flows of nearly 2 weeks in early by mid-21st century and as much as 1 month by the late 21st century. So perhaps pretty much consistent with what we saw as the output of the HBV or process-based model. And the addition of some physics to the LSTM now should at least intuitively improve our trust in the modeling results. And what is worrisome is that the large divergence in behavior between models that produce comparable results in standard out-of-sample prediction and true out-of-sample prediction. This requires a more in-depth understanding and appreciation of the value of domain knowledge. Because true out-of-sample prediction is nothing but extrapolation beyond the observed data and behavior used in model development and calibration. So extrapolation is our challenge, and my understanding is the only way to tackle this extrapolation challenge is to really embrace the knowledge base available rather than pushing it away and embrace a data science type approach that basically divorce from that knowledge base. So to wrap up, I'm going to show this slide only. What is typically ignored value of domain knowledge in deep learning? This is very important to understand and embrace. What is knowledge base? Knowledge base is a set of principles modulated via conservation laws like mass, energy, and momentum, and process parameterizations, which represent our perceptions of how two or more variables might be related. And you could see that across three fronts: conservation laws, monotonicity and rates, and feedback mechanisms. And I'm giving just some examples for what each of these means. Conservation laws like continuity equations in hydrology are built to ensure that water balance is preserved in simulations over time. And because of that, so when we develop a process-based model, we're pretty sure that water balance in the model is right because there is a differential equation in that accounting for it. But in deep learning models, it's not the case. They do not automatically account for such laws. And as a result, water can falsely introduced or lost in the course of simulation when you use a deep learning model. Second one, monotonicity and race. What do I mean by that? So again, we have some knowledge on how different variables are related in the nature based on the cause and effect mechanisms that we are aware of. An example from thermodynamics is that we know that the relationship between melt rate and available heat is monotonic, of course. So it means more heat causes a higher melt rate. We also have some rough estimate of the feasible range of this rate of change. But deep learning derives such relationships entirely from data, all from scratch, ignoring that knowledge base. And in cases, it might come up with non-monotonic relationships because they have enormous degrees of freedom and they feed to errors to data. And then you might get, for example, non-monotonic relationships for things that you are for sure know that they are monotonically related. And the last one here that I'm bringing up is feedback mechanisms. As an example of that in hydrology is what we see in water vegetation, coupled water vegetation systems, where precipitation, available soil moisture, and plant biomass interact in complex ways over time. So the knowledge-based models, the process-based models can account for these feedback mechanisms in the way that you develop differential equations, ordinary or partial. But in deep learning, there is no way to account for those things explicitly or even implicitly. And that becomes very important in long-term, in the simulation of long-term dynamics when you don't have data to constrain your model. So of course, all I said was to try to motivate you on the next topic, which is how to bridge deep learning and process-based modeling. And that is not something that I can cover here. And the thing is, doing it is still very embryonic, but has great potential in the age of big data and computational power. But if you want to read more about it, you could refer to the paper that I showed at the beginning. Again, it's here. So it reviews the current methods for this bridging, which are, I believe, still very embryonic. And also, we are working on a follow-up piece on how machine learning can really revolutionize earth and environmental sciences. And in that, we are trying to really think outside the box and see how we can bring the two very different paradigms together. So I think I've been speaking a lot for almost an hour. Thank you very much.
Thank you, Dr. Razavi, for your nice, motivational, and inspirational talk. I myself feel like I am more like a process-based type of modeler, and I am eager to jump into learning deep learning uh, type of models for sure. So we have during your session over 80 people now. There are 75 people connected, and we have a lot of questions. So we are going to take some of them, and I will ask Jorge to start showing you some of the comments and questions of the auditorium. Thank you again, Dr. Razavi.
Thank you.
So first of all, thanks for the presentation. We are really glad to have you here. So our questions are mainly, the first one comes from Daniel Julian Lancheros. The question is, based on the principle that geographic and hydrological data needs good machines demanding with respect to resources to work, how do you think that the size of the files could be controlled to perform machine learning?
Hey, could you repeat the question again?
Based on the principle that geographic and hydrological data needs good machines to work, how do you think that the size of the files could be controlled to perform machine learning? The question was made by Julian Lancheros.
Okay, I'm not sure if I get the question right. Yeah, so you're talking about machines. You mean by machines, you mean computers or algorithms?
Yeah.
So what I can say, hopefully I'm responding to the question. Of course, we are in the age of big data and computational power, and you might say that, okay, we are just building bigger and bigger computers and bigger models, and when you look at models compared to models of 10 years ago, they have become much more bigger, much more computation intensive, and much more data demanding. But it's not clear where we are headed, and we are just eager to go for bigger and larger. And when you ask people, modelers, why would you do so, they say, okay, because we have computational budget available. And for example, when you, in hydrology context, when you talk to people who go for hyper resolution hydrologic modeling, and still in terms of data, we are not in the age of big data in those type of analysis, because still we don't have high resolution, for example, soil moisture data or precipitation or climate variable data, but they have gone farther than data available, and they do very fine resolution hydrologic modeling. And when you ask them why, they say, oh, because we can, because the computational power is available. But I mean, there are of course trade-offs. And you know what, I think one point that I'm trying to elaborate here and in my talk is that as scientists, we shouldn't get easily overexcited about technology, and we have to make sure that we have some guiding scientific principles, and we have to follow them. We cannot easily abandon, for example, Occam's razor and say, hey, we have computational power, why would you go for a simpler model? While the simpler model can still very well explain that phenomena that we are working on, because we have computational power. Typically now we go for a complex model. So anyways, hopefully I answered the question.
Thanks for the answer, Mr. Saman. The second question was made by Nicolas Duque Gardiazabal. He asks, as sensitivity analysis can find tipping points in the inputs of models that produce consequence of detrimental or beneficial interest, how do convey those thresholds to decision makers using graphs? And how can we reveal those models' interaction, give certain behavior that produces those effects?
Okay, I see 2 points or questions here. One is about tipping points. The other one is about the interactions. So, of course, I'm not an expert in resilience and tipping points, but based on what I know about these dynamical systems, theoretical things, identifying a tipping point and predicting a tipping point in a system is is not easy. And typically what you see in the literature, after the tipping point has happened, then scientists go and evaluate that. And typically we haven't been able to predict tipping points easily. And in hydrology, and as scientists, we don't generally expect to see tipping points because we believe hydrologic systems are dissipative systems with one equilibrium state. There is no multiple equilibrium state. But as soon as you couple hydrology with ecology, for example, then you see some. Yeah, and I've seen some work in the context of sensitivity analysis trying to identify tipping points. So my understanding is those type of works are still embryonic. They are very helpful because I mean, one of the early indicators of tipping points based on the literature is that the sensitivity of things with respect to each other change significantly, and things become sensitive to more sensitive to some forcing or perturbations. And I haven't read a lot about that, but I've seen, I think, a couple of papers trying to use sensitive analysis techniques to do so. I'm not sure exactly how they work, but still very embryonic. That's what I could say. In terms of explaining those to stakeholders, I would say even explaining those to other scientists is not easy at all. Very complex theories, and there is a lot of uncertainty in those. I'm not sure how we can explain that to stakeholder, while we cannot easily even communicate about that among ourselves. About interactions, again, very similar. Of course, research around interactions between different things in sensitivity analysis context has some meat. So there is a wealth of literature on that. So that's of course much easier to understand and explain. That is, again, very important because interactions can change over time. And that is what we should be aware of, and we should try to quantify. But that is also the part that is perhaps still a bit of a research gap, how to understand the interactions may change over time and be able to explain those to stakeholder, for example, because these interactions typically may give rise to unintended consequences because you typically don't see the interactions at the surface. These are at deeper levels, deeper layers of a problem.
Thanks for your answer. The third question was made by Camila Garcia Echeverri, and she asks, in Colombia, there are so many hydrological variables that are not adequately measured. For example, evaporation, evapotranspiration, recharge, even runoff. How to proceed when training information is scarce?
Yeah, that's a very good question. And you know what? It's not only the problem of Colombia, it's the problem of Canada as well. And you know what? So data in Canada is very sparse. And, so you might know that I have Iranian background, and I worked in Iran for some years on hydrology as well. And when I moved to Canada, I was quite surprised because technically what Canadians say in terms of hydrologic data collection, we are like third world countries. And the reason is clear. So the country is very large and the population is very small. So how much you can invest really on that? So we deal with same sort of problems. There is in particular tremendous uncertainty in our forcing data in climate variables like precipitation. What can we do? Again, going back to the topic of this presentation, data-driven modeling versus process-based modeling, I would say the knowledge base could help us still because we have our own methods for gap filling and prediction in engaged basins based on the knowledge base available. But I would caution people to just rely on deep learning or data-driven type modeling per se for regions where data is more scarce than normal. And of course, there is no easy solution to that. And yeah, so you might remember we had prediction in engaged basin initiative that ran for 10 years. Hundreds of papers got published, but you know what? Yeah, we didn't solve the problem after all those research efforts. So it's going to remain a major issue, at least for the 10, 20 years from now.
Yes, I think the same. We have time only for two more questions, so we are going to go with the question made by Camila Gordon. Camila Gordon, she asks, if deep learning models are based on historical data, how to model in a context where climate is constantly changing?
That is exactly the point that I'm trying to raise with this talk. So let me be honest. So here is my history with deep learning. I started my research career in my master's thesis with neural network back in 2003. And back then we were in the previous wave of popularity of ANNs. And I worked on neural networks, deep learning stuff for some years, but I abandoned those around 2010 or so because of problems with these. So these techniques could work very well in some contexts. For example, in image recognition, as you see on your cell phone, or for your Siri in iPhone, natural language processing. But in hydrology context, we have to deal with non-stationarity, meaning your training data might be way different than what you might see in the future. If you haven't seen some particular behavior in the past, then your model is not informed about those type of possibilities. Your model might be way off. But just recently, if you look at the literature of deep learning, and particularly in hydrology, you might see some claims or exaggerations of the power of deep learning in solving these things. So I certainly agree with that. I mean, I'm not saying that deep learning wouldn't be able to help. Definitely, there is potential, but we shouldn't get overexcited, and we should find ways to bridge knowledge base and deep learning. If you could introduce those knowledge base principles into deep learning, then you might come up with a new paradigm that could work under those unseen conditions. But we are there yet, so that area is still very embryonic.
Yes, and finally, we have a question from Jonathan Rodriguez, and he asks, what do you think about the use of convolutional neural networks for representation of the two-dimensional variables in hydrological domains?
Yeah, so convolutional neural networks, as far as I know, are very powerful tools for image recognition, because they can basically go layer by layer, and if apply multiple filters on top of each other and try to extract some features from images. And basically that's what's happening in your smartphones, for example, when your smartphone sees you, for example, opens unlock or whatever. So definitely that technology could be applied, for example, in image processing that we get, for example, from satellite images or airborne images when we want to process them automatically. So that is the obvious application of those technologies. But beyond that, I've been thinking about that myself. How could we use that sort of approach to solve some hydrologic problem? I don't know. What I thought of initially was that perhaps that could help us address the scale issue in hydrology, because when you look at convolutional neural networks, basically all you do is scaling at different layers. So you upscale, downscale, and by doing that at different layers, you try to extract features from images. So to me, that relates to scaling, but how could you do it? I don't know. But I've been thinking about that myself, and if you have any idea, I would be happy to discuss. That might be a very good breakthrough in the field of hydrology, bringing some ideas from machine learning.
So we had so many questions, and I don't know if we can send the question to you in the future, Saman, so you can answer them by email or by any method.
I'll be happy to remain engaged with you guys, sure. And you know what? Yeah, you could compile them and send them to me, or people could directly email me, and we go from there. And yeah, if you have ideas, I mean, I'm still on sabbatical for another 6 months or so, so I'm going to have some time to think and discuss new ideas, and I'll be very happy to do so.
Ok, so a la audiencia que estamos teniendo actualmente, vamos a recopilar sus preguntas. Vamos a crear un Google Poll, Google Forums, para que ustedes ingresen sus datos, para que el conferencista Saman nos ayude a responder las preguntas y se las mandaremos a ustedes en el futuro. So, Mr. Saman, we are really glad to have you here. I'm going to connect Erasmo here. So, first of all, we have been delighted to have you here. A lot of thanks to you, and thanks to the audience for coming into our audience. So, thanks to all.
Thank you, Saman, again. It was really nice to having you here. The promise is to try to have you here again in the following months. So the promise to the audience, perhaps you will have another talk, maybe in sensitivity analysis, or maybe a follow-up of this one. And for sure, we can still collaborate and do some things together. Thanks to the audience, and we hope to see you in the March talk that we don't know still what the conference will be about. Thanks again, and goodbye.
Thank you very much for the invite. It was a pleasure.